So next chapter is work and energy. What is work? What is work means? In general, when we talk about work, we say when we do something, we said we do some work. In physics, we define work as energy transfer by force. So in physics, we define work as energy transferred by force. So what is energy? Energy is ability to do work. So work is energy transferred by force. So the energy is ability to do work. So force is push or pull. And we learn how to calculate the push or pull using Newton's second law. Net force, which is a vector, is equal to mass times acceleration. So energy transferred by a push or pull or force is work, and energy is ability to do work. We're going to derive a couple of equations for work and also work energy relationship in next few slides. So far we talk about kinematics equations. There are 8 equations, 4 equations for one direction, and another 4 equations for perpendicular direction to the first 4 equations we wrote, and then we learn Newton's second law, which says net force is equal to mass times acceleration. These are vectors because acceleration has a vector, therefore net force has a direction, therefore vector. Work, we use W for work, which is equal to force times displacement. Okay. So here we use letter S for displacement. It's same as the displacement we talk about, but we use a special character S for displacement. But some textbooks you see if X, we know displacement is delta X, which is final position minus initial position. Displacement is a vector. Force is a vector. How about work? Is it a vector or scalar? Because every time when we talk about vector, if for this case, force is a vector because acceleration is a vector. Here, force is a vector because force has a direction, and also displacement. Displacement also has a direction. So when you multiply two vectors, it become, there are two different vector multiplications, but when you do a vector multiplication, sometimes you will get a scalar. So work doesn't have a direction, but you have force and displacement, both have direction. So, but when you multiply these two, you will end up getting we call it dot product. You will get a scalar. So if you want to get the units of work, which is units of force, which is Newton. Unit of force is Newton. We know Newton. We know Newton is kilograms meters per second square. So everything is inside Newton. And also units of displacement is meters. So Newton meter, we call it joule, Joule, and uppercase J we use as a notation. So 1 Newton meter is equal to 1 joule. So Newton meter, force times meter is distance. Newton meter, it's a standard international SI unit. And there are two other systems, CGS and BE. So in CGS, we use dyne for force and centimeter for distance. So dyne times centimeter, we call it Earth. And in BE, British system, we use pound for force and foot for distance, foot pound. We use in BE system. So the very first equation we learn is work is equal force times displacement. But make sure when you use this equation, you have to have force and the displacement in one direction. In this example, we have a bag, this traveling bag, we apply a force along this direction, which is 30 degrees to horizontal. But bag moves from here to here. It's in horizontal direction. So therefore, you have to have the component of force along this horizontal direction. So we learn how to get using trigonometric relationships. If you take cosine theta, which is equal to adjacent, let's say adjacent, which we don't know, divided by hypotenuse, which is force. Therefore, the side we don't know, the length of the side we don't know, we need the horizontal component, which is this length, horizontal, or the side of this triangle, this side, which is unknown. We put a question mark, which is equal to force times cos theta, cosine theta, F cosine theta. So F cosine theta, so instead of force, you put the component of force along horizontal direction, and the displacement is S. So F cosine theta, the theta is angle. It can be any angle with respect to this horizontal line multiplied by the displacement. If the force is 45 newtons and the angle is 50, F cosine of this angle is 45 cosine 50 times the displacement, which is 75. We will substitute these numbers into this equation. This equation, F 45 cosine theta angle is 50 and S displacement, which is 75 meters. You will get, make sure when you apply these, you have to have the right units, SI units. SI units of the displacement is meters. SI units of the force is Newton. So if you have Newton meter, then you can write your final answer 2170 joule or Newton meters. Okay, in this example, the first figure says when you lift something, you apply a force along F direction, vertical direction, and also it travels on the same direction, F and S. Therefore, the angle between the direction, force and S. In the previous case, we discussed S is in this direction, and you apply a force to the suitcase is in this direction. So this angle is 50 in the example we did before. So if the F and S are in the same direction, this angle becomes 0. Therefore, F cosine 0 times S. So cosine of 0 is equal to 1. So therefore, F times 1 times F. Therefore, F is. In the second case, force is still this way. This is the direction of the force because we still hold in the weight, but it travels this way. Therefore, angle is 180. So cosine 180 equals -1. F times -1 is negative F times S. Therefore, Fs. If force and the displacement are opposite direction, then you get negative Fs. Okay, here's another example. Again, you have to calculate the work W, which is equal to F cosine theta times S. If the displacement and the force is in the same direction, this term become 1. Therefore, work equals force times S. So displacement is given is 65 meters, but force is not given, but instead of it says acceleration is there, which means we can calculate this force using this acceleration. How are you going to calculate the force? Net force we know from Newton's second law, which is equal to mass times acceleration. So mass is 120 kilograms and acceleration is plus 1.5 meters per second square. So now you know the mass, force, sorry. You can substitute force here, and S is 65 meters, and now you can calculate W. Okay, let me give you a example. We learned that work is force times displacement. Notice S is displacement. In previous chapters we use X, so X and S both are exactly the same. Okay, it's just a notation. So let me do an example. Let's say we have a flat surface and we have a object, and we apply a force F1, 50 Newton, another force F2, 30 Newton, F3, 20 Newton. Okay, so let's say it move to this location. F1 is still 50. So let's assume it moved to this location, and this distance is S is 30 meters. Okay, so W equals force times S, which is, this is the equation. So S is 30. How about F? Remember, when we talk about work, we always use force and direction in one direction along one line. So if this object moves from here to here, it's vertical. So therefore you have to consider only these two forces because those are in horizontal plane, and you ignore this force because that is a vertical force, and because of that vertical force it's not going to do any work. Even if you lift it up, it doesn't going to move this way, so this force not going to contribute to work. So therefore the net force is 50 Newton, which is in this direction, and then there's another one 20 Newton. So our resultant vector or net force is 30 Newton. So the work total force is 30 Newton. We know it's to left, and then 30 meters, which is this, and this is so when you do the work, calculate the work, make sure you calculate the net force along the direction it travels and ignore these forces because that force is not going to contribute to work. Okay, so this is the equation I used in the previous example. Work, net force, and displacement. So we know Newton's second law, force is mass times acceleration. Okay, so therefore I can write W equals, instead of force, net force, we can write mass times acceleration, M-A-S. So we know S is displacement, so W is M-A-X. There's a reason I put X instead of S, because you can ask why I change S to X. There's a reason I will show you in next slide why I wrote X instead of S. The reason I'm going to write X instead of S is we learn kinematic equations. V final square is equal to V initial square plus 2 times acceleration times x. So this term in parentheses, acceleration times x, is the displacement. So if I replace, then you have ax. So from this equation you can solve for ax, which means you can bring this v0 to this side and divide by 2. So ax, if you solve for ax, you have v final, which is this, minus v0 divide by 2. So ax is half v final square minus v0. So now I'm going to substitute this ax into this equation. W is equal to mass times, instead of as, I'm going to write half mass times half v final square minus v0 square. So if I multiply v final square and v0 square, to get rid of this parenthesis, I get half mv final square minus half v0 square. So half times mass times speed square or velocity square, we call it kinetic energy. Okay, it can be initial square velocity square, then we can say initial kinetic energy. If I put final, we can say half mv final square is final kinetic energy. Okay, so kinetic energy Ke is equal to half mv0 square. Okay, so now we have two equations for work. We just we in previous slides we learned work is force times displacement, and we just learned another equation to calculate work, which is equal to half mass V final square minus half mass V initial square. Okay, so this is kinetic energy, this is work, so therefore we call it work energy because it has kinetic energy Ke final. Ke final, this is kinetic energy final. F means final. This is Ke initial, initial kinetic energy. We call this work energy theorem. So here's an example. So the mass of the space probe is 474 kilograms. So we can write down the information given. So mass is 474 kilograms. So initial speed or initial velocity is 200. V naught is initial velocity, 275 meters per second. And if 56 millinewton force acts, so force is 56 milli. So milli means 10 to negative 3 Newton. Make sure when you work on problems, you have to work with SI units. So Newton is the SI unit of force. So milli, you have to convert to 10, Newton. So milli convert to Newton, you have to convert, multiply by negative 3. And the displacement S is given, which is equal to 2.42 times 10 to 9 meters. And the question is, what is the final VF? So we learn a equation for work which is equal to net force times displacement. So force times displacement. Force is given, displacement is given, which is equal to half mass 474 V final square, we don't know V final, which we're going to calculate, and half m V naught square. So V naught is given 275. Force times S is given. So force is, let me use a different color. Force is 56 times 10 to negative 3. And displacement is 2.42 times 10 to 9, which is equal to half. Mass is 474 kilograms. VF square minus half 474. V initial is 275 square. So when I substitute, you have only one unknown, and then you can solve for V final. And next two slides show how to solve for V final. So here you says W equals net force times displacement, which is equal to half mv final square minus mv naught. V naught is initial, final, and then you substitute the parameters. So then you have V final, which is the only unknown, and you can solve for that. Okay, so far we learned how to calculate the work if something is moving on a straight line. So work is equal to net force times displacement, or we learn another equation in terms of kinetic energy of mv final square minus half mv naught square. If an object moves in a horizontal plane, if we know the final velocity and initial speed or initial velocity, v final, if you know the mass, v initial, mass m, and the displacement s, we can use this one of these equations. Actually there are two equations. Work is equal to force times displacement, and also final kinetic energy final minus kinetic energy, which is half mv naught square. So we can calculate one of those unknowns. And now I'm going to ask, let's say we have an object sitting on a flat surface. In previous chapters, we learned mass, let's say 10 kilograms. This object has a weight force pointing downward, W, which is called weight, and we know which is equal to mass times gravity. 10 kilograms times 9.8 meters per second square, so 98 Newton. And also we know if it is on a flat surface, there's a normal force from the surface on this mass m, Fn, which is same as W, which is equal to 98 Newton. So now if you want to lift this object and bring it to this level, let's see. So if you want to lift it and move to this level, now you have to work against so we have to overcome the gravitational force 98 in order to move up. So next few slides we're going to learn another equation for work we're going to do against gravity. Okay, so gravitational potential energy, the work we do against the gravity, W. This is the general equation we learn. W equals, if cosine is the angle between the force and the direction it travels, if the same direction, cosine theta becomes 0, which is equal to 1. So cosine 0 equals 1. If the angle between force and displacement is 0, cosine 0 equals 1. Therefore, W is equal to force times displacement. So force is force against the gravity, which is gravitational force. And the displacement is, if this position is final position and if this is position is initial position, this is the distance it traveled, h naught minus h final. Notice most of the time when we talk about previous equations, we always use final minus initial. Here h naught is greater than hf, and this equation is a little bit different. Final is this value. So initial height minus final height. So force is gravity force mg, and the displacement is h naught minus h. This is s. This is f. Force is gravity. Therefore, we call it gravitational potential energy. W gravity mg h naught minus hf. So this is the second equation. We learn another equation, kinetic energy final, half mv final square minus half mv naught square. This is kinetic energy and this is gravitational energy. So there are cases we do work against the gravity and also we have kinetic part. So like a projectile motion. So we go above the ground, we have a height. Therefore it has a gravitational part. And also since it's a moving object, it has a potential energy. It has a final initial speed and a final speed, or it has, if you consider two events, it has initial and final, which means work due to kinetic and work due to gravitational. So there are cases we see the combination of gravitational and kinetic. So we're going to discuss how we can combine these two and write another equation combining a case which has kinetic energy and also potential energy. Okay, so let's consider this example. Gymnast leaves the trampoline at an initial height of, this is h naught, is 1.2 meters and reach a maximum height, this is hf, before falling back down. What is the initial speed of the gymnast? So this is the question. What is the speed when he leaves the trampoline? We know when he reaches his maximum height, V final becomes 0. So now we have two equations we learn from kinetic and potential. W is equal to half mv final square minus half mv naught square. So, and also we learn another one, gravity is equal to mass gravity h naught minus hf. So this side is same, therefore I can write half mv final square minus half mv initial square is equal to mg h naught minus hf. And there are some common terms like mass. If you divide by m, so all three terms, the two terms on the left side and the single term on the right side has m, therefore I can cancel m. So, and also v final is 0, this is 0, therefore you have only one equation, negative half v naught square is equal to g h final, h initial is 1.2 minus h final is 4.8. So from this equation you can solve for v naught and you can find the initial speed. Okay, in previous slides we learned how to write work, which is equal to force times displacement, and then we made another equation for force and displacement using this square minus half mv initial square. So we call it kinetic energy is half mass velocity square. And last time we learned another, in previous slide we learned another equation for gravity, work against gravity, mg h naught initial height minus mg final height. So going to learn another one. We call it potential energy. Oh, since it's against gravity, we call it gravitational potential energy. PE is equal to mass, gravity, H. So you can put F or initial depending on final or initial. So initial gravitational potential energy and final gravitational potential energy. In general, we write mgh just like this, half mv naught v. It can be initial, it can be final. So but in general we can say half mv square for kinetic energy and mgh for potential energy. So again the units is joule of potential energy because it's units of energy, and force times distance. This is gravity force, weight, mg, times displacement. So therefore, same units.